The idea of total probability allows us to partition problems into manageable sizes. The particular problem of interest, of course, depends upon the nature of the problem. A consequence of total probability is our ability to reverse the direction of conditioning. Some context first. So, let's start with some abstract probability space, some sample space omega. And imagine that we have a partition of omega into a finite or countably infinite number of events, a sub j. We will think of the probabilities of these events, a sub j, as the a priori probabilities of a chance experiment. These are the probabilities that one starts with before the experiment is actually performed, before we see anything. Probabilities before the fact. We imagine, as we've seen repeatedly in our examples, that the probability measure is implicitly specified via certain conditional probabilities. A conditional probability of some target event H given some prior or side information A sub j. We will think of these in a natural sense, as we will see shortly, as forward or transition conditional probabilities. From a purely mathematical point of view, we think of this as starting with some A sub j and then proceeding to an H. The question now is, what happens, what can we say about the conditional probability in reverse? What is the probability of an A sub k given an H? Now the setting is something like this. It might be fruitful to imagine that the A sub j's represent a partition, an input to some probabilistic system. For example, imagine mobile telephony, imagine digital communications, where the A sub j's could represent symbols that are transmitted one after the other. For example, the A sub j's could represent the letters of the English alphabet, A, B, C, D, up through Z. The a priori probabilities reflect the intrinsic or natural frequency of these letters in that alphabet. For example, the letter E in the English alphabet occurs about 13% of the time, an excessively large proportion of the time, in ordinary conversation in written language. The letter Z, on the other hand, appears very infrequently, about 0.07% of the time. So these represent the a priori probabilities. We'll assume they're known. We can infer them from the problem. Imagine again that we are transmitting a letter. We receive some letter, but the transmission medium is noisy. It is imperfect. So we receive a letter, let's say H. I don't necessarily mean the English letter H, but an event H representing some symbol that is obtained. And the transition from a transmitted symbol AJ to a received symbol H has a certain probability, a conditional probability of H given AJ. We will very naturally, in terms of this diagram, think of this as a forward conditional probability, or if you're thinking of it dynamically, a transition probability. These, we assume, are known to us, are given to us. For example, from an understanding of the physics of the problem, or the biology of the problem, or perhaps purely on mathematical modeling considerations. The question at hand is this. Again, keep in mind, let's say a communication example. A symbol has been transmitted, a symbol has been received. Once the experiment is done, once the transmission has been done, the receiver has a symbol in hand. And her burning question is, what symbol actually was transmitted? In other words, she wants to reverse the direction of the problem. She says, given that a symbol H is in hand, what are the chances that a particular symbol AK was transmitted? If we can compute these reversed probabilities, these are naturally called the a posteriori probabilities, probabilities after the fact. Then, in principle, we could figure out what is the most likely symbol which was originally transmitted, given that a particular symbol was received. Okay. Now, how does one go about doing something like this? Well, naturally, we're given the a priori probabilities, we are given the transition probabilities. Our natural instinct is to partition the sample space according to the events A sub j, in our example, the symbols that were transmitted. And then total probability allows us to write down the probability of obtaining any of the received symbols simply by addition. So far, so good. This is now readily computable given the information we have in hand. Our question is, how do we reverse the question? Well, by the definition of conditional probability. The probability of an event AK given H is obtained as a ratio. The joint probability of these two events divided by the probability of H. But we can decompose the probability of H in terms of the a priori probabilities, in terms of the forward conditional probabilities, and then we now get an expression which looks like a chaining formulation. And you'll notice that on the right, the only terms that appear are the a priori probabilities and the forward conditional probabilities that are known to us. We now have an explicit mechanism for reversing the direction of conditioning. This formulation is called Bayes' rule for events. Now, at a high level, a student will be well advised to not memorize the formula, but understand how it was stitched together. At work is simply the principle of additivity, the principle of total probability. And experience will then allow her to stitch reversed probabilities together.